Good morning. Let's start assignment 7, the contour integration. Integration from 0 to infinity, sine of mx over x into x square plus a square dx is equal to pi over 2a square 1 minus e the power minus ma, where m and a are real positive. So let's start with the proof. In the numerator, I'm having sine of mx. So we will integrate fz is equal to, in the numerator, this will become e the power iota mz, right? And the denominator will be, this is x into x square plus a square. So this will be z into z square plus a square. So we will integrate this fz along C, where C is a contour indented at the point. Now here, if you take the denominator equal to 0, you will get z equal to 0 and plus minus a iota. Please remember, we have to indent the contour at the points that are present on the real axis. जो points real axis के ऊपर present होंगे उन्हीं के ऊपर indent आएगा, और real axis के ऊपर z equal to 0 हमारे पास यहाँ पर point है. When we take denominator equal to 0 and the poles are given by z equal to, yes, 0 and plus minus a iota, of which a iota lies inside C. Just wait. The poles is z equal to 0 and plus minus a iota, of which only z equal to a iota lies inside C. Right? Okay, so now next step is we have to find the residue at this pole. So the residue of fz at a iota is equal to e the power iota mz. I'm taking this z with the numerator so that the differentiation of the denominator becomes easier. So I'm taking this 1 by z with the numerator, and I have to take d by dz of z square plus a square. This is the formula for calculating the residue at z equal to a iota, right? So this is equal to e the power iota mz over z over the differentiation will be 2z at z equal to a iota. Now put this point z equal to a iota here. We get e the power, yes, this is a iota and iota square is negative 1. So this is minus ma over minus 2a square. Very fine. Now next step is, by Cauchy's residue theorem, integral over whole contour fz dz is equal to 2 pi iota times the calculated residue, and that is e the power minus ma over minus 2a square. And now we have to split this contour into so many integrals. Just look over here. We have first integration from minus r to minus rho. Then we have integral over the semicircle gamma, then from rho to capital R, and then along this this semicircle tau, right? So first from negative r to negative rho, this is negative r to negative rho, right? And then along the semicircle gamma, and then from rho to r, then the semicircle tau. So whenever we integrate along the real axis, we have to write here f of x dx. And then for gamma, I have to write f of z dz. Again, then along the real axis, I have to write f of x dx. And then for semicircle tau, I have to write fz dz, which is equal to this, alright. This is negative. I have taken this negative sign outside, and 2 will be cancelled out. So this is negative pi iota e the power minus ma over this a square, right? Okay. Now let's find the integration for this semicircle gamma for the limit rho tending to 0. For smaller semicircles, we are having rho radius which should tend to 0, and for the larger, that is only 1 tau semicircle, the capital R, the radius of that semicircle, should tend to infinity. So what is the formula for this? It is iota times 0 minus pi, that is theta 2 minus theta 1, and limit z tends to, where it is indented, at 0, right? Then z minus 0 f of z. And then I'm writing, this is minus pi iota and then limit z tends to 0, this is z itself, and fz is e the power iota mz over z into z square plus a square. Cancel this z, and then this is minus pi iota limit. Okay, let's put z equal to 0 over here now. Put the limit over here. This will e the power 0, this will become 1, and here it is, denominator will be a square. So this is minus pi iota over a square, right? Now for this integral we have calculated. For this integral, I know that this integral is along tau, and this function 1 over z into z square plus a square is tending to 0 uniformly as z tends to infinity, and also this is meromorphic in the upper half plane as it has no singularity there. So by Jordan's lemma we know that this integral will be equal to 0, right? So this integral, this dz, this is 0, which means limit r tends to infinity. Can I write this as f of z dz because it is fz only? So this is equal to 0. Now letting r tends to infinity and rho tends to 0 in 1. In this 1, we get, if this r tends to infinity, this will be from minus infinity to, this rho is tending to 0. So the first integration is from minus infinity to 0. And then we put the value of this integral, and then we add this integral from 0 to infinity, and then this is 0, right? So this will become minus infinity to 0 f of x dx, and integral over that semicircle gamma is, we have calculated, that is minus pi iota over a square, plus then it is from 0 to infinity f of x dx, and this integral is 0. So this is equal to minus pi iota over a square e the power negative ma. Taking this pi iota over a square to the other side and merging these two integrals together, I get minus infinity to infinity, putting the value of fx, which is e the power iota mx over x into x square plus a square, writing fz in terms of fx. So this is dx, and then this is equal to taking pi iota over a square common, and this will be 1 minus e the power negative ma, right? Okay, what we need in the numerator, we need sine of mx in the numerator for that integral, which we have to prove. So we have to equate real parts or imaginary parts now. Yes, we have to equate the imaginary parts, right? So equating the imaginary parts, when we equate the imaginary parts, we get sine in the numerator. So this will become minus infinity to infinity sine of mx over x into x square plus a square dx is equal to pi over a square 1 minus e the power minus ma. And because this is even function, so the integral will be from 0 to infinity twice sine of mx over x into x square plus a square dx is equal to pi over a square 1 minus e to the power negative ma. Can I take this 2 to the other side in the denominator? Yes. So taking this 2 here now, we get the required result. Thank you so much. God bless you all.